Common causes of piping vibration, factors leading to instability in pipe systems. We'll explore about flow-induced turbulence, mechanical excitation, pulsation, high-frequency acoustic excitation, surge or momentum changes, cavitation and flashing. Overview and importance. Piping vibration is a critical issue in process industries because it can lead to fatigue failures, leaks, and catastrophic ruptures. These failures pose significant safety hazards, including the release of hazardous or flammable fluids, which can result in fires, explosions, and environmental damage. Additionally, vibration-induced fatigue can cause unplanned shutdowns, leading to costly production downtime and expensive repairs. The root cause of these problems lies in the dynamic stresses generated by oscillatory motion within piping systems. Unlike static loads, dynamic stresses fluctuate rapidly, accelerating material fatigue. Traditional piping design codes often overlook vibration considerations, making it essential for engineers to understand the mechanisms behind vibration and incorporate preventive measures during design and operation. By identifying common causes of vibration, operators can implement proactive strategies to mitigate risks, improve reliability, and ensure compliance with safety standards. This presentation will explore the most prevalent sources of piping vibration, their characteristics, and the conditions under which they occur, providing a foundation for effective management and control. Flow-induced turbulence mechanism and impact. Flow-induced turbulence is one of the most common causes of piping vibration. It occurs when fluid flow becomes turbulent, particularly near discontinuities such as valves, tees, reducers, and bends. These components disrupt the smooth flow of fluid, creating eddies and vortices that generate broadband kinetic energy. Although this energy spans a wide frequency range, most of it is concentrated at low frequencies, typically below 100 Hz. Low-frequency excitation can cause visible movement of pipes and even pipe supports, leading to structural fatigue over time. The severity of turbulence depends on factors such as fluid velocity, density, and system geometry. High flow rates, often resulting from debottlenecking or relaxed erosion velocity limits, exacerbate turbulence and increase vibration risk. Turbulence-induced vibration primarily affects flexible piping systems with long unsupported spans, where natural frequencies align with the excitation range. Preventive measures include optimizing piping layout, using long-radius bends, and ensuring adequate support near turbulence sources. Understanding this mechanism is crucial for designing robust systems and avoiding costly failures. Mechanical excitation sources and characteristics. Mechanical excitation originates from rotating and reciprocating machinery, such as pumps, compressors, and engines. These machines generate dynamic forces that can directly load connected piping or transmit vibrations through shared structural supports. Reciprocating and positive displacement equipment are particularly problematic because they produce significant harmonic content at multiples of their running speed. If these harmonics coincide with the natural frequencies of the piping system, resonance occurs, amplifying vibration levels dramatically. Even centrifugal pumps and compressors, though generally smoother, can induce vibration when operating near surge or stall conditions. Mechanical excitation issues often arise in systems where piping shares supports with vibrating machinery or where structural stiffness is inadequate. Preventive strategies include isolating vibration sources using anti-vibration mounts, adjusting machine speeds to avoid resonance, and reinforcing pipe supports. Understanding the interaction between machine dynamics and piping response is essential for mitigating mechanical excitation and ensuring long-term reliability. Pulsation, pressure fluctuations, and resonance. Pulsation refers to dynamic pressure fluctuations within the process fluid, which can lead to severe vibration when amplified by acoustic resonances. Fluids in piping systems exhibit acoustic natural frequencies, forming standing wave patterns under certain conditions. When excitation frequencies from pumps or compressors align with these acoustic frequencies, pressure pulsations intensify, creating large shaking forces at bends and reducers. The most common sources include reciprocating pumps and compressors, which inherently generate oscillating pressure waves, and centrifugal compressors experiencing rotating stall at low flow conditions. Additionally, flow-induced excitation can occur when vortices form at deadleg branches. Intrusive components, or thermowells, producing periodic disturbances. These mechanisms often interact with structural natural frequencies, resulting in resonant conditions that amplify vibration. Preventive measures involve pulsation analysis during design, installation of pulsation dampeners, and careful control of operating conditions. Understanding pulsation dynamics is vital for avoiding fatigue failures and maintaining system integrity. High-frequency acoustic excitation characteristics and risks. High-frequency acoustic excitation occurs primarily in gas systems downstream of pressure-reducing devices such as control valves, relief valves, and orifice plates. These components generate intense acoustic energy due to turbulent mixing, shock waves, and high-velocity impingement, especially under choked flow conditions. The resulting vibration typically affects the pipe wall at frequencies between 500 and 2000 Hz, exciting shell flexural modes that produce localized dynamic stresses. These stresses concentrate at circumferential discontinuities like small bore connections, welded tees, and supports, making them highly susceptible to fatigue failure. Acoustic fatigue failures can occur rapidly, sometimes within hours of operation, posing significant safety risks. Preventive strategies include using low-noise valve trims, increasing downstream pipe length for attenuation, and reinforcing vulnerable connections. Acoustic excitation is a critical consideration for safety-related systems such as relief and blowdown lines, where failure consequences are severe. Surge and momentum changes due to valve operation effects. Surge, commonly known as water hammer, results from sudden changes in fluid momentum caused by rapid valve operations. When a valve closes abruptly, the kinetic energy of the moving fluid converts into a pressure wave that propagates upstream at the speed of sound. This transient pressure can reach magnitudes far exceeding normal operating conditions, imposing large dynamic forces on pipework and supports. Similarly, rapid valve opening can induce momentum changes that generate significant vibration. Surge events are particularly hazardous in liquid systems, where incompressibility amplifies pressure spikes. Preventive measures include controlling valve actuation speed, installing surge tanks or arresters, and using specialized relief devices. Understanding surge dynamics is essential for designing systems that can withstand transient loads and avoid catastrophic failures. Cavitation and flashing mechanisms and consequences. Cavitation occurs when local pressure within a liquid drops below its vapor pressure, forming vapor bubbles that collapse violently as pressure recovers. This process generates intense localized shock waves, causing noise, vibration, and erosion damage to components such as pumps, valves, and orifice plates. Flashing is a related phenomenon where liquid undergoes a sudden phase change to vapor due to pressure reduction, producing large forces and flow instabilities. Both mechanisms introduce transient excitation into the piping system, increasing fatigue risk and reducing equipment life. Preventive strategies include controlling pressure drops, using anti-cavitation valve trims, and staging pressure reductions across multiple devices. Addressing cavitation and flashing is critical for maintaining operational reliability and minimizing maintenance costs. Summary and key takeaways of common causes. Piping vibration arises from multiple mechanisms, including flow-induced turbulence, mechanical excitation, pulsation, high-frequency acoustic energy, surge, cavitation, and flashing. Each mechanism has distinct characteristics and risk factors, but all share the potential to cause fatigue failures and operational hazards. Effective management requires a proactive approach encompassing design optimization, vibration analysis, and preventive maintenance. By understanding these causes, engineers can implement targeted solutions such as improved support arrangements, pulsation dampeners, low-noise valve trims, and controlled valve operations. Ultimately, mitigating piping vibration enhances safety, reliability, and efficiency across process industries.